Okay, let's get started. So in this unit, we've been considering feature selection, where the idea is motivated by overfitting. If you use too many features, your variance goes up and increases your mean squared error. And so on the other hand, if you ignore too many of the features or use the wrong ones, you're going to have high bias. So that's going to be a problem. And so you want to figure out the exact subset of features that helps you best for prediction. And so that's the feature selection problem. And we talked about several approaches to that. But now we're working on the main approaches we'll focus on, which is ridge regression and lasso. And these are both based on the idea of regularization, where you take the cost function or the loss you're interested in working with, which until now for us has been RSS, and then you add to it what's called a regularization term, and you minimize the sum. And the regularization term is designed to somehow help you in a way that you would need help if you used the original loss alone. So our current motivation for what we need help with is we want this term to somehow guide us in choosing the right coefficients, which in this case means setting a subset of the beta predictors to 0, because when beta j is 0, we are not using feature xj. So we want to set the right combination of betas to 0. And we said we're going to consider two types of regularization, although there are many, many others out there. These are the most common. One is based on penalizing the sum squared coefficients, and here we have an adjustable parameter alpha that we can tune via cross-validation. That's one option called L2 regularization, because this thing is the L2 norm. And then we have L1 regularization because this thing is the L1 norm. This is sum of absolute. And this picture gives us a hint about how they're going to behave. Basically, the squared penalty used here is not going to be very sensitive to small deviations in beta j from 0. And so as we'll see, it's not going to help us directly with feature selection. However, it is going to help us with something else. Whereas the L1, you can see that any change from 0 will directly increase the regularization term. And so the regularization term, by adding it here, it gives us an incentive to set all the beta j's individually to 0 unless they are helping us reduce our RSS sufficiently to justify them being non-zero. So that's the idea behind these. And we're not applying regularization to the intercept term. And also, we talked about one other thing before, is we talked about standardization. Actually, maybe we talked about this. Sorry, we talked about this after. In standardization, we subtract the mean of the sample mean of the features and the target, and we also divide by the sample standard deviations. And this is used because if the features have very different values, we expect the beta j's to have inversely different values. And so if the model had some gigantic beta j's and some small ones due to changes in the feature size, this wouldn't work well because this treats all the beta j's the same. Okay, so we're going to use standardization anytime we use regularization. And as a byproduct of this is when you subtract the mean from both the samples and the features, the intercept term, the least squares intercept term, becomes 0. So this is sort of a simplification. Because it's 0, it simplifies our models that we write down. In practice, we never really have to worry about that intercept term. We know it's 0. And so that's what we're going to do also. Just assume we use standardization. All right. Any questions on anything we've done so far? Okay, great. So now we can move forward and get into some details. So here is our regular old RSS cost. here's our L2 regularization term. We add them together to get what is known as ridge regression. I don't really know why it has that term, ridge, but that's what it's called. And another way to write this more succinctly, let me ask this, is Ryan Zhu here? Yeah. So do you remember how we wrote RSS in terms of the squared L2 norm?
Not off the top of my head.
Okay, so we have vector y minus vector x, or sorry, matrix x times vector b quantity squared. This is the 2 norm, or standard norm. And now, as we saw, or as I hinted in the previous page, the second term is going to be the squared 2 norm regularization. Okay. Is Yingzhe Zhang here? So why am I using the X matrix in forming Y hat and not the A matrix?
So the beta 0 is equal to 0, so the first.
Exactly.
Is
Right. Right, because so actually when we create the beta vector now, we're even leaving out the beta 0 term. It's not even there. Whereas traditionally it had always been there because we use it as the intercept term. So now we know it's going to be 0 because we're doing standardization. We define the beta vector as the remaining terms, and they multiply the feature matrix without that ones column. Okay, great. So that is ridge regression. And then LASSO, which stands for least absolute shrinkage and selection operator, is RSS using the same norm plus alpha times the 1 norm, the L1 norm of beta. So we put a little subscript 1 down here to distinguish the 1 norm. And we talked about these before, if you remember way back on the second lecture, I believe, when we talked about linear algebra. L2 norm is the way you measure distance as a straight line between 2 points, as the crow flies, they say. Whereas L1 norm, you measure distance by the traveling only in the coordinate axes. So in 2 dimensions, if you're a taxi cab driver in Manhattan, you cannot drive diagonally through the blocks. You have to go down 1 block, turn down another block, and so on. So you would measure distance using that L1 norm. Okay, so these are the two new cost functions, regularized cost functions that we are going to focus on. Okay, any questions? Okay, great. So let's start with ridge cost. So y minus x beta squared plus alpha times beta squared. Okay, so one of the nice things about the ridge cost is that you can compute the coefficients in closed form. And you can figure out this expression using a derivation very similar to the one we did back in Unit 2. By setting the gradients with respect to all the individual beta coefficients to 0 and solving for the beta vector that sets that gradient to 0, you get this expression. So the difference, if you notice, is this term. And in fact, if you think back, like if I'm just doing least squares, I would set alpha to 0, right? Because I wouldn't have this term. So now if you look at what happens in this new equation when alpha is 0, you get rid of this and you get exactly our least squares solution that we derived. So what is changing here is this, the addition of this new component here. Okay. Often there's a homework problem that gives you some practice in deriving this or something similar. Okay, so now we would like to understand what does ridge regression do, like what are its characteristics. So a super useful tool visually to understand what happens is called the coefficient path. And the coefficient path is the plot of the individual beta J coefficients versus the regularization strength. So in this unit, we have the demo, which is predicting log PSA levels from these different biometrics. And so each of these lines, these are the beta coefficient values versus alpha. So when alpha is very small, like as alpha goes to 0, we know that this just gives us least squares, right? So when you look far to the left, notice this is a log scale. When you look far to the left, you see that these values converging to some values, right? As alpha gets small, that's the least squares solution. Least squares solution is basically the limit, and it's already very close to the limit. You can see how they've flattened out. Okay, so that's one extreme. On the other hand, what's the other extreme? Well, it's as alpha grows to infinity. As alpha gets super large, essentially what happens is that this term gets much larger than this, to the point where when you want to minimize the sum, you focus entirely on minimizing this. And the way to minimize that is simply to set beta to 0. Okay, so when you look at very large alpha, you see it's kind of converging to this trivial solution where all your prediction coefficients are exactly 0. Okay, so obviously this is not a very useful solution, and least squares alone, you know, we're already done discussing least squares. It has certain issues, so this is not interesting. What is interesting are the intermediate values of alpha. As you increase alpha, the overall behavior you notice is you notice the coefficients shrinking, getting closer to 0. But, you know, interesting things happen. You can see that some of them change sign. So here's 0. Like some of them start negative and become positive. You know, it's not like they just all shrink directly to 0. It's like there's some interesting things going on in between. You get it, you know, kind of a range of different non-trivial solutions in between. But if we're interested in feature selection, that means we really want the beta J's to go exactly to 0. And the only time that happens with ridge is asymptotically as alpha goes to infinity, right? So for no finite alpha, do we see, I mean, okay, yes, like you can see like this brown coefficient pass through 0 at one point, and this pass through 0, but like at no point do you tend to see multiple coefficients going to 0 and really performing feature selection with ridge. Okay, so if our goal is really feature selection, we don't want to be using ridge. Is that making sense? Yeah. For feature selection, we want to drive like a bunch of the beta J turns exactly to 0, and at that point we're ignoring those corresponding features. So here that's not really happening until you get to the trivial solution where they're all 0 at infinite alpha. Okay. Okay, any questions on this? All right, so then you might be wondering, well, why are we even talking about ridge? Here we're in a unit on feature selection. Why are we talking about ridge? Well, there's a couple of reasons. Number one, it's relatively simple. It's one of the only regularizations where you can derive something derive the betas in closed form. But actually, there is something very useful about it. It is the go-to method when your different features are highly correlated, meaning you have different features that are almost redundant. If you had the same feature repeated twice, you would say that they would be perfectly correlated. So in practice, that probably doesn't happen, but you might have two that are very similar. And here's the issue. When you have two features that are very similar, and you look at this matrix, this is a D by D matrix that shows basically the feature. It's not exactly the autocovariance matrix because we're not, actually it is, because we said we subtracted the mean from all the features, right? So this is actually the autocovariance matrix in this case. And what you would find under feature correlation, This matrix is going to have some eigenvalues that are very small, close to 0, and other ones that are large. And when you invert this matrix, those small eigenvalues get very large because their inverse is large. And as a result, some of these beta coefficients, or maybe all of them, get very large. Okay, and so you might say, all right, what is the problem with large prediction coefficients? Well, when you think about how the prediction is done, you're taking your test feature vector, you're doing an inner product or multiplying each test feature by the corresponding beta coefficient, summing them together. And if these are very large, they amplify noise basically like noise and outliers and things like that in X. And so as a result, your estimate is sensitive to aspects of X that you don't want, as the noise, and you basically get overfitting. Okay, so the reason that ridge regression helps is you're penalizing alpha times this for some alpha. And so you're basically saying, on one hand, I want you to give me something close to least squares, but in doing that, I don't want you to ever make the beta coefficients very large because I'm going to tell you to penalize the squared value of each. So as a result, it helps to reduce the size of the betas and therefore reduce overfitting. So that's why people use this in practice. That's why it's important. And it is a very practical and well-used technique. All right, so I'll describe a little example on the bottom, but before I get into that, are there any questions? Is it making sense, sort of what we're doing here and why we're doing it? Any questions from anybody? Okay. Question? Yeah.
We are still considering the standardized data, right?
Yeah, all through. The reason why it's important here is because, this regularization, again, is treating them all the same because it's sort of weighting them the same amount. So it works best with standardized data. Yeah. Okay, any other questions? Okay, so there's a demo. You can click on the green link here that I created for this. It's simple. It's just to show the point. There's only 2 features in this demo, and I constructed them synthetically in such a way that they're very highly correlated with each other. And so here we have the coefficient path on the left, alpha, variation versus alpha, and look what happens. Oh, and by the way, the true values of these coefficients, the ones I used to construct the data, are plus and minus 1. Okay, so like in an ideal case, our betas would be plus minus 1. But of course, our model doesn't know that. It has to use the data to estimate the betas, to train the betas. And so the least square solution, which you can see as alpha is very small, gives us values of like minus 30 and minus 32, right? That's way different from plus and minus 1. And that is a result of this correlation getting, basically, the noise is getting amplified because the beta coefficients are very large. So as I increase alpha, you can see the coefficient values for this range of alpha here are actually very close to the true values. Right? Now, if I go beyond and I use an alpha, a regularization weight that's too large, as we expect, they both go to 0. So that's not useful. But what is useful is alpha in this range. We're really getting close to the truth. Okay, and this is all with ridge regression. So now you might ask, well, okay, great. Like, because we know the truth is plus minus 1, we can see that this alpha in this range is what we want. But how in practice do I find that alpha? Well, we use cross-validation. The standard cross-validation we learned about, you could do, I can't remember what I used here, but k-fold cross-validation, where you break up your training set into some folds you use for training and then some you use for testing. And you can make a plot of the cross-validation mean squared error versus alpha. And this is what we see. Starts out kind of high because of the variance problem. And then it gets low, and it's actually low in this range of alpha, which sort of corresponds to what we want to see here. And then as I increase alpha and my coefficients, converge to 0, bias takes over, and I have really bad performance. And that's expected, and not an issue because we probably, we don't want those values anyway. So according to cross-validation, we know that what we do is we search over a grid of alphas to find the lowest cross-validation mean squared error, and it tells us to use alpha of about, the value of about 10. And for that value of 10, you can see we get almost perfect agreement with the truth. So here we see ridge regression coming to the rescue, least squares doing, giving us inflated values which increase the variance of our performance. So you can see this is the difference between least squares and ridge regression with cross-validation. So we get a boost. Our mean squared error is going down. Okay, is this making sense? Okay. Any questions? Okay. All right. So this is ridge regression. So now let's move on to lasso. Lasso, if you remember, we have y minus x beta squared. That's our RSS plus alpha times the L1 norm of beta. And so unfortunately, this is not a problem that you can solve on paper analytically unless you have a single feature beta. In that case, you can do it, but if you have two or more features, which is the dominant case in practice, you have to solve this numerically. Now, fortunately, this is what's known as a convex optimization problem, which is something we'll study in Unit 6. But what's nice about convex optimization problems is that the solutions are computable. Now here I wrote easily. I don't know, maybe I should qualify that because there are definitely algorithms to do it, but they're somewhat expensive. When you compare the cost of this problem versus like the cost of ridge regression, you might find that this is like 10 times or more complex computationally. So probably more even, 10 to 100 times more complex. So yes, you can compute them, but there is a cost. Okay, and in Lasso, it gives us a bunch of algorithms to do this inside the Lasso method. So as we'll see, we use this Lasso method exactly the same as we used our linear regression method. So since we know how to use that, we know how to use Lasso. But we have to wait a little bit, especially if the problem is big. Our computer's going to take a little while to crunch through the data. Okay, so that's the first point. The second point is, well, how does this behave? Let's look at the coefficient path, which we have on the right. So what we notice is that as we increase alpha, as before, when alpha is very small, we get least square solution. So least square solution is somewhere like that. And similar to before, as alpha gets very large, this doesn't matter. And the right thing to do to minimize this cost is to set everything to 0. Okay, that's not interesting. But what is interesting is what happens in between. And you can see that as alpha increases, one by one, the coefficients turn off. So for example, for this alpha, all the coefficients are non-negative or non-zero. But at this alpha, this brown one has turned off. And then you go a little bit farther to here, then the pink one has also turned off. And then you go to here, and the brown, pink, and green have all turned off. And so one by one, the coefficients are being turned off until you get to this region where there's only one coefficient left, LCA vol. And so this, from like a science perspective, would tell us that Lasso is suggesting that this is the single most important predictor of PSA of these 8 different biometrics. And it would say, well, if you have to choose 2, it should be this blue one and this dark purple one here. I don't know, maybe it's SVI, and so on. So it tells us, it kind of ranks the importance of the features. So that's the first thing we see, is that there's these non-zero, or fewer non-zero beta j as you increase alpha, which is doing feature selection exactly how we want. Any questions about that? Is that sort of clear what's happening? Right. Of course, as before, we have a bias variance trade-off. So for the small alphas, we have least squares. We're using too many coefficients, our variance is too high. On the other extreme, if I turn off all my coefficients, I'm going to have terrible bias problems. So the question is in between, which gives me, which alpha is really going to be best? But it turns out that things are a little bit more complicated than that with lasso. And that has to do with a second thing you realize when you look at this plot, is that not only do the features one by one get turned off, but the prediction coefficients, they shrink towards zero, right? So like here, you can see that the value that you use for LCA vol is much smaller than at lower alphas. So this is shrinking towards zero. They're all shrinking towards zero, right? And this is going to be a form of bias. It's like a systematic error, and that lasso is telling us not only do we turn off a subset of the set to zero subset of betas, but also it's telling us to shrink the values of a bunch of all the betas remaining. And this is a problem, and this will reduce our performance. So we're going to have to figure out some ways around this. Okay, but those are the main two things we see, is that features are going exactly to zero, great. Features are being shrunk towards zero, not great. That's bad. Okay, questions on this? Is this making sense? Okay. So, so again, we can use it for feature selection. That's great because we have beta j is going to zero. It's just a matter of figuring out what value of alpha to use. But the remaining non-zero betas shrink towards zero, which gives bias. And so what we really want to do is keep only the indices of the non-zero coefficients, meaning the set of integers, like, I don't know, if these were each an integer like 0, 1, 2, 3, here we would be selecting, this integer, and this integer. So 0, 1, 5. Okay, so that's what I mean here. This script J lasso is the set of J such that the beta J's are non-zero. So that is relevant information. That tells us exactly which features we should be using for prediction. But we want to somehow ignore the beta values lasso gives us. So what we do is we actually just run standard linear regression with the lasso selected features. So in other words, as a first pass, we run lasso, we figure out which beta j's are non-zero, and then we remove all the other features from our data set and we run least squares using the feature reduced data set, just the features that lasso told us to use. Two-stage procedure. Is that kind of clear? Okay, and the reason least squares works for this is because we learned that least squares is unbiased. At least, assuming we have the right set of features, it has no bias. So that's essentially the procedure. And so the key question now is, how do we choose alpha? What are the details of cross-validation? And so this is a little bit tricky, so I'm going to actually show you 4 different approaches to doing this. The first 2 approaches are not recommended. I'll call them naive. And then 2 recommended approaches. But it's still useful. We'll still learn a lot as we go through them, and that's why I'm showing you these naive ways. Okay, so let's dive into the first approach, which is implementing and tuning biased lasso. So by biased lasso, I just mean this original technique that we would be running here. Okay, so we're doing scikit-learn's lasso method. So let me point this out. So in this line, you can see I'm instantiating my linear model.lasso. So similar to what we did with least squares linear regression. And then we have basically two approaches. This is the manual approach. This is using 2 for loops just to understand what's happening, the details of it. So we have an outer for loop here and an inner for loop. And this is very similar to what we saw with model order selection, where we had an outer for loop over the folds, and there we had an inner for loop over D, the model order, the number of features we use. So now we actually don't have discrete things. We're choosing a continuous parameter, alpha. And so this is how we do it. We create a logarithmically spaced grid of alphas. It's important that it's log spaced because we really need to span a very wide range. Here we're going from 10 to the power minus 3 to 10 to the power 1, so 4 orders of magnitude. So we create this log spaced grid, and so in the outer loop we go through our different folds, and on the inner loop we go through that grid of alphas. And so basically what we do is we compute this sample mean squared error for every combination of test fold K and hypothesized alpha A. And then we do the sample average to compute the sample, the mean, sample mean, SMSE, and the standard error for each alpha. Okay, so it's very similar to what we did with model order selection in D, but now instead of a grid of Ds, we have a grid of alphas. Okay, so that's basically this first approach. Is that making sense, what we're saying to do? Okay. Now, this is how you would do it if you want to see all the details, but this is a very common procedure in machine learning. So scikit-learn gives us this grid search CV where you can do this in basically 2 or 3 lines. So here's the main grid search CV command. You have to give grid search CV, and so what it does is it does cross-validation over your grid of alphas. You have to tell it what is your estimator. In this case, it's the lasso estimator. You have to tell it what are the grid of parameter values you're sweeping over. And this is going to be, it's saying, okay, change lasso's alpha parameter and use this particular array. What style of cross-validation do you want to use? So here we created this k-fold cross-validation thing separately up here. K-fold cross-validation where we tell it how many splits and we tell it to shuffle the data. And finally, we tell it, when you're doing this cross-validation, what criteria do you want to use? What is good performance? What is bad performance according to you for this problem? And so the way that scikit-learn structures it is that high scores are always better. And if you think about mean squared error, it's kind of opposite, right? We want mean squared error to be low, not high. So the way that scikit-learn does this is they use negative mean squared error. And now negative mean squared error, you want to be as large as possible, right? As close to 0 as possible. So that's how they handle mean squared error as a score, negative mean squared error. Okay, so basically you tell it all that information and then you do fit, and it runs through all your folds and it runs through all your alpha hypotheses, and it fills out this matrix, and then it computes these averages, and then all you need to do is extract them. What's the mean test score? It gives you an array. Here we're negating that negative to get mean squared error. And then here's the standard deviation of the test score divided by square root k minus 1 to get our standard error. Okay, so this is how you're going to be doing it in practice. You probably don't want to be spending the time to write these for loops. You just want to be, using grid search CV, one of the most important commands of the term. Okay, is that pretty clear? Okay, so here's the problem with this. There's actually two problems, and they're both caused by the bias. So essentially, this is saying, among this range of solutions here, find me the alpha which gives the best mean squared error. And the trouble with that is we know that this is shrinking our coefficients, so we're faced with this trade-off between wanting to select the right coefficients but wanting not enough shrinkage. And so as a result, it's going to give you the wrong alpha value as it's trying to navigate these two kind of conflicting desires. So you might say, okay, rather than using bias lasso, let's do this two-stage procedure where we tune lasso to figure out the subset of coefficients that we want to use, and then we debias it using least squares. We run least squares on the coefficients selected by lasso. So let me describe what's happening here. So you essentially use the procedure on the previous page to choose alpha by cross-validation. And so you could minimize, you could choose the smallest mean squared error, or you could use the one standard error rule. Either one is fine. Probably this works a little bit better. So now you've figured out alpha, then you run lasso on the full training data. You don't need to split this into different folds anymore. You can just use the full training data. You compute the lasso coefficients. And now you look through them and you find all the ones that are non-zero. That tells you which features lasso wants you to use. In this case, it wants us to use 7 out of the 8, most of them, but it tells us which one not to use. And finally, we isolate those features, so we basically get rid of the one, and now we run least squares. Okay, so that's the overall procedure. So essentially, we run this to get our alphas. Then in this command, we just run lasso fit after telling it the alpha we want to use. And okay, and so this gets rid of some of the bias issues. Yeah, I think I've described everything here. So this is an improvement for sure. In fact, like if you look at the cross-validation mean squared error, this is what you get if you use the bias lasso coefficients, and this is what you get with least squares, debiasing, and you can see the mean squared error has gone down. Not a huge amount, but it's gone down. But this is still not what we want. Does anybody see the problem here? See what's not ideal about this? How bias is still affecting us?
Bias is still influencing which features we end up selecting?
Yes, but do you see exactly how? What parameter is affected by? Exactly. So when we chose alpha, the alpha we chose was really chosen according to this trade-off between not shrinking too much and selecting the right features. So we want to get rid of that. So the better approach is to think of lasso plus least squares as sort of that procedure as a whole should be tuned. So we want to know what is the alpha such that if I run lasso with that alpha, then extract the feature indices and then use least squares on those, what is the best alpha for that unified procedure? And there's basically a couple ways we can do this. The first way, which is a little bit simpler, is to run a for loop. And so it goes like this. This is a little bit manual. So here we have a for loop over our alphas. And then in the for loop, we choose the alpha, based on the for loop index. We run lasso. We figure out which are the non-zero coefficients. We then essentially we're essentially training our least squares linear method on those coefficients, and then, in this case, storing the mean squared error. And so when you look at the plot of mean squared error, cross-val mean squared error versus alpha, you can see that it has this kind of stair-step behavior. Okay, so let me ask, is Jiawei Liang here? Okay, what about Sirach Gench? What about Bird Green? About Daniel Kowalski?
Yeah.
Okay, so any idea why this is behaving in this stair-step manner?
No.
Okay, so let's think back to what lasso does as alpha is increased, right? So as alpha is increased, you can see that it is basically turning off one coefficient and then another coefficient and another coefficient, right? So you go through these areas of alpha where nothing changes from the subset perspective. And so if nothing is changing in terms of the subset, least squares will give us the same solution for all the alphas in that range. And therefore, it gives us the same cross-validation mean squared error. So that's why it has this stair-step behavior. And so in this plot, what I'm showing is the one standard error rule. So we have the mean squared error, and then above it, I'm basically looking at one standard error above it, and then we run the one standard error rule, which is basically find the simplest model within one standard error of the optimal model. So here's the optimal model. One standard error of that is this level. So what's the simplest model there? Which way do we have to go to find simple models? To the right or to the left? Right, so as alpha in the back, yeah.
To the right, because you're taking out part of the...
That's right. As alpha grows, we shut more coefficients off, which means that the model gets simpler. So we actually would want to use something like this alpha, because this is the one that's the best within one standard error. Okay, so when we do this, we see that, yes, in fact, we have improved from the previous page. Things are getting better. Okay, so this is one way to do it. It's actually the most, it's relatively computationally simple, but something about it is still cheating a little bit from the cross-validation perspective. Does anybody see where the cheating is? So in cross-validation, to do really proper cross-validation, the test data, there should be some test data that we never use to train our model, that we use only to evaluate it, right? And the trouble is, we don't, so we fit lasso using basically all of our data, and then we're doing cross-validation later. So you could say this is not quite right because you're using all your data for model order selection or for feature selection, and then you're later on doing cross-val to compute the MSE. So there is an alternative that is a bit more proper, and that is to use grid search CV. But for this, we need a fancy new tool that scikit-learn gives us called a pipeline. So it goes like this. Let me focus on, this is the grid search CV. Oops, sorry. This is the grid search CV line here. And as always, you have to tell it what is the estimator, what are the parameters, what's the k-fold, what's your criteria. So if you think about our estimator, the thing we're doing, it's really not just lasso, it's lasso plus least squared as like a cascaded unit, as a composition of functions. So how do we build that thing in scikit-learn? We use what's called a pipeline. So in scikit-learn, you can build a pipeline. You can kind of build a block diagram almost where you say, do this, and then do this, and then do this. And think about that as one unit. Here, we're calling that unit pipe. So in this case, the two things we're doing is we're running lasso, and then we're using this select from model to extract the subset of coefficients lasso finds, and then we're using least squares on those coefficients. So here's the pipeline, first lasso, then least squares. So once we have that as sort of a computational unit, we just give that to grid search CV, and that's it. Everything else is done here in a couple lines. And the results are a bit different than what we saw on the previous page. So here, what's interesting is that we don't have the stair-step behavior. Every alpha we considered here is giving us slightly different performance. This is also going to be a lot more computationally intensive because there's a trick we can play here. As we move from one alpha to the next, the lasso method, it's an iterative algorithm. If we start it at the location where we stopped previously, it has no work to do if nothing changes. So it's very fast, and it basically just has to solve the lasso problem like a handful of times. But over here, we have to solve the lasso problem many, many, many times, one for every alpha. And so as a result, and not only that, but we have to run, it ends up being quite a bit more expensive for that reason. So the results are, I think in the end it chose the same model, 388, 373. Yeah. So basically, when we do this with one standard error rule, it gave us the same performance as before. It's just an alternative approach. It is really the proper cross-validation approach because we are never using the test data for designing our model, either for choosing alpha or for choosing the beta coefficients. It's really a clean separation of test and training. Okay, so that's the 4 different approaches. You can see it's a little bit intricate. And any questions on these? Okay, so until now we've talked about a whole bunch of different methods to attack our demo, which this demo definitely benefits from feature selection. So let's now look at them all together in perspective. So first we have plain least squares, what we learned about in Unit 2, no feature selection. The mean squared error is 0.403. Exhaustive least squares. So this is not often tractable, but in this case, since we only have 8 features to the power 8, it's reasonable, we can actually do this. Exhaustive least squares gives us 388072. Then we have these sequential feature selection. So this is the one where we, I think I used backwards search where you start with all the coefficients, all the betas, then pull one out one at a time. This one actually worked equally well. It's not always this case, but in this case it gave us the same features as the optimal procedure. Now we have this mutual information-based or univariate technique. This one you can see not working very well, not recommended. Next we try ridge regression. It turns out for this data set, feature correlation is not the problem. It's more of a feature selection issue. So ridge also doesn't perform well. It's the second worst. When we run plain lasso, it has coefficient bias, so it's actually even worse than ridge. When we debias it with least squares, that was the second naive method, we definitely get an improvement, but it's still pretty bad. Then we have the for loop and the pipe methods. They are not as good as the optimal, but they are very close, 4th decimal position. And this is just what happened for this data set and for this choice of random seeds, because if you run this demo several times, you will get different random seeds that are used for the k-fold splits, and the performance can actually change as you run at different times. So yeah, this is just an example, but it's pretty typical of what you will find in practice. Okay, so is this sort of making sense? These different approaches, feature selection, some are optimal, most are not, and we see behavior kind of like what we'd expect. Okay, so that kind of concludes the part of this unit that is going to be useful for the lab. The next part is framing all of what we've done until now in the course from a more statistical perspective and learning about the maximum likelihood and MAP procedures. How many people have heard of maximum likelihood? Okay. And what about MAP? Maximum a posteriori. Okay. So these are super important methods. In some sense, they kind of unify the way that people think about machine learning in general. So what we're going to argue now is that when we think about machine learning, we want to think about estimating statistical parameters in some probabilistic model of the data. Until now, we haven't done that. We've basically just worked with heuristic methods. Like we said, let's minimize squared error, right? Let's do that. And we can do that because it's something we can do easily. But I think some of you guys have asked me, but why are we working on squared error? What if there's outliers in our data? Does squared error do well with outliers? And the answer is no. It collapses when you have outliers in your data. And so then you might ask, well, then what's the justification for using squared error? When would I know to use squared error? When would I know not to use it? And so this statistical framework answers those questions for us. What we do is we make statistical assumptions, probabilistic assumptions on different parameters. And then we say, for those assumptions, what's the right thing to do? What does statistics tell us is the right thing to do? And what we will learn from this, we will learn exactly when we want to use least squares and when we don't want to use least squares. We have to think about it from another perspective, and then it will be clear. And so this gives us the maximum likelihood, or the maximum likelihood procedure, ML, gives us that. And then what's interesting is MAP actually explains regularization. It explains ridge and lasso from another perspective. It's kind of like an enhancement of ML. Okay, so that's what we're going to do next time. I think we're pretty much out of time for what I want to get into, so we'll save this for next time. But yeah, what we're going to talk about next is really just one of the most important concepts from the trial. So have a good weekend. I'll see you guys on Monday.